Hello, everybody. Good afternoon. I am Dr. Mendenhall, and today we are hosting a scientist from Lawrence Livermore National Lab by the name of Dr. Marcus Worsley. He is a research staff scientist there in the Material Sciences Division, and he's going to speak about his work on aerogels for energy and environmental applications. Thank you, Dr. Worsley.
All right, thank you for the introduction and for the opportunity to speak today. I actually was I was sad, with the whole situation with COVID that I could not come out and see you guys in person and be able to visit and see, facilities and see everyone in person. One, because, I've never been to Morehouse College before, so I'd love to visit the campus. But I also have a lot of family and friends in the Atlanta area. And so I was, hoping also to be able to visit with them. So hopefully at some point when COVID passes over and we get past this and get a vaccine, I can, actually come back and do an in-person visit there at Morehouse. So to start off, I just wanted to give a quick introduction of myself, as Juana mentioned, just to kind of give you guys an idea as to how I ended up landing here at Lawrence Livermore National Lab, working as a staff scientist. I actually, and this is, I hopefully this story I think will be significant to the undergrads and seeing the impact that you guys can actually make on, younger students when you go back home. I actually decided to be a chemical engineer when I was about in the 4th grade, and that's because when I was in the 4th grade, I was told I had to do an interview of someone that I know to find out what they do, what their job's like, and write a little report on that. And there was this a brother who had graduated from college. Had moved to the town in which I was living in Michigan, working for one of the big chemical plants. And, because he wasn't from there, my parents had, kind of taken him in and kind of adopted him as, a son. So he's kind of like an older, a much older brother to me at that point. And so I decided to interview him. And so he was telling me, about his job. He was actually a plant engineer and was a chemical engineer, and was the one who basically, the way he described it was when anything went wrong in the plant, they would call him. And this could happen, any time of day or night, on the weekends. This was in the 90s. So, he carried a pager, or late 80s, early 90s. So he carried a pager, which, I thought was kind of cool. But to me, it sounded like, a Superman. And that, anything went wrong, they called him and he came in, and really, really fixed it. And so, I asked him, I was like, well, what do you have to be good at in order to do your job? And he said, math and science. And incidentally, those are the only subjects I actually liked in school. And so, kind of at that point, I kind of set him as like, okay, that's what I want to do. I want to be a chemical engineer. And so, that was really my trajectory in terms of, my major when I ended up going to college at Michigan State University. While I was at Michigan State, and this is why I would also advise you guys to definitely, do internships, explore many different opportunities. I actually had the opportunity to do an internship at a 3M plant outside of Chicago and work with, plant engineers. And really kind of see what they do on, a day-to-day basis. And it was at that point that I realized I did not really want to be a plant engineer. A lot of the engineers, their jobs really, this was for a masking tape plant for 3M. Masking tape is kind of one of their cash cows. And the main mantra that they had was that, don't change anything. Everything has to kind of operate within, these specifications. And so, when I saw that, I was like, well, that does not look like fun. And fortunately, the job I had was actually working on a research and development tool, a printer, a coder that they had there. And so we had, different vendors coming in, wanting to try new things and to tweak, recipes. And that actually turned out to be the thing that I thought was much more interesting. But at that point, I didn't actually even really think about grad school. I was thinking about maybe doing a master's. And it wasn't until they had this program that actually was in Atlanta at Georgia Tech called Focus. It's called the Focus program that runs over Martin Luther King Jr. weekend. And it's really to try and, sell undergrads on going to grad school. And, they brought a whole bunch of, Black, Latino students from all over the country to kind of learn about the PhD process, meet a bunch of Black, PhDs, go to a whole bunch of, seminars and talks. And they also informed me that, you would get paid to go to grad school, which, really, I didn't realize that. I thought all grad schools like, law school or business school, you had to actually come out of pocket. And so I was like, really that opened my eyes to the possibility of actually getting a PhD, and seeing that, this might be something that would interest me, knowing that, as a PhD, you'd really be doing more of the research, much more of a research focus. And so that is what, really shifted me in terms of wanting to go to grad school and pursue my PhD. So when I graduated from Michigan State, I was fortunate. I applied to Georgia Tech, of course, but that summer before I went to, the summer after I went to the Focus program, I got into a research program at Caltech, and came and saw California for the first time, which, coming from Michigan, kind of blew my mind in that, all summer, it would never rain. They would plan things, months in advance. And I'd be asking, well, where's the rain date? What happens if it rains? They're like, you're clearly not from here. It doesn't rain here. And, and Caltech also just had a beautiful campus. And so I, pretty much decided, okay, California is another place. I definitely want to go someplace warm. So I applied, Georgia Tech, Caltech, and those were the two main ones. Oh, and Stanford as well. And Stanford's one I ended up going to for my PhD, working with a professor there in the chemical engineering department. And then from there, after actually seeing what, the PhD process was like, and academia, because originally I did want to be a professor, but after kind of seeing, firsthand how difficult it is, the tenure track, my hat's off to, professors. It is a tough road. It's a very hard job. But at kind of that point, I wanted to do something a little bit different. And so that's how I ended up, landing at Lawrence Livermore National Lab. My advisor was kind enough to help me, pursue that different career path, and, introduced me to one of the scientists here, who gave me an interview, and, I was able to start. And so I've been here now since 2006, so about 14 years. And I really enjoy it. And I enjoy also the fact I do get to work with professors at various universities, such as, Professor Mendenhall at UC Berkeley, UC Santa Cruz as well. Lots of very close collaborations. So I think with that, I can go to the next slide. If it'll let me move slides here. All right, there we go. So that's how I ended up here at Lawrence Livermore National Lab. If you're not familiar with the National Lab system, within here, within the United States Department of Energy, this schematic will give you a general picture for how it's organized. There's a number of labs here that are very focused on very specific problems or areas of science. And then you have much more applied science labs, which is where Lawrence Livermore National Lab is focused. And our angle in looking at applied science is more geared towards security, national security interests. So this is looking at, of course, defense, but also things like energy security, protecting the grid, making sure that, our materials that go into things like, batteries, electronics, that we have secure, nationally secure sources for these sorts of things. So we're multi-purpose, but clearly with a national security focus. If you were to come out here, our lab is built really like a campus because it was originally established as and managed really by the University of California. And so established back in 1952. Currently, we have around 6,000 employees, and we're actually doing quite a bit of hiring. So that is rising. As I mentioned, we're organized like a campus. And so, we have about a square mile of space in which we have a lot of different facilities, that cover, physics, chemistry, engineering, really all of the different biology, all of the different disciplines, as well as all the supporting facilities, operations sort of programs as well. And then about 11 miles away, I'm sorry, about 10 or 15 miles away, we have a experimental test site. Because as I mentioned, we do quite a bit of work with weapons here. And so we have a test site for testing those. A lot of explosive sort of work goes out in that area near Tracy. And then lastly, we have we're funded by the government to the tune of around $1.53 billion. Here is just a breakdown of how that money is really divided up in terms of organizations within the government and the various programs. So as you can see, the vast majority of work does have to do with weapons, and the vast majority of that really has to do with taking care of and managing the aging nuclear arsenal. A lot of those, the nuclear arsenal was really, built back in, a lot of those devices were built in like the 60s, and they were not expected to have the lifetimes that we're now expecting of them. So it takes quite a bit in order to keep those devices safe and to make sure that, if we did need to use them, they are actually going to be functional. But it also deals with things such as safeguards and security. So, securing the weapons, and then the non-proliferation. So we also have a significant chunk of our budget that supports the people that do go out and do the testing, do the monitoring for when there are, nuclear disasters such as at Fukushima, but also when you have bad actors in the world that are trying to actually proliferate nuclear weapons, or there's some, black market sort of attempts to move or transport nuclear weapons. There's a surveillance involved with that that we're working on. And then in addition to that, we're funded by the Department of Energy, Science and Engineering. That's a lot of the work that I do, which is in the area of energy and the environment, Homeland Security, and the Department of Defense. If you were to look at the different what we call core competencies here, or the areas of research and development that go on here at the lab, this is how we are organized. You have, energy density science, which has a lot to do with, explosives and nuclear weapons. You also have advanced materials and manufacturing, which is where I sit, and that a lot of that focus for me has really been on energy storage sort of materials, as well as energy conversion, so catalysis. And then advanced manufacturing. So we do a lot of very custom and groundbreaking 3D printing sort of techniques here. We also have bioscience, bioengineering, nuclear, laser and optics, I'm not sure if you're familiar with the National Ignition Facility. It's basically one of the largest laser facilities in the world. And so that's a large thing for which we are pretty well known. Earth and atmospheric sciences. There's a lot of climate modeling that's actually done out here that actually takes advantage of our high performance computing simulation and data science group. We, at any point in time, typically will have, at least 2 of the fastest computers in the world here at Lawrence Livermore National Labs. It's one of the things that we're also very well known for. And so a lot of the work that I do, though, is really focused on advanced materials and manufacturing, but also leverages some of the computing power that we have here as well, which I'll go into. I left this outline in here. I'm probably not going to get to everything on this, just in the interest of time. But I did want to go over aerogels to give introduction to those who are not familiar with those particular materials. And then much of the talk really will be focused on energy storage, as well as the 3D printing that we do of our aerogels to address energy and environmental sort of concerns. Excuse me. So aerogels are really what I consider very novel materials, and their various sorts of properties. They're typically made up, one way to think about them really is as a foam. They're very low density. They're made up of nanoparticles, and they have various regimes or size ranges of porosity. So if you were to look at this little cartoon here, if you look at an aerogel, one very familiar or common architecture is this kind of a string of pearls morphology, in which you would have a nanoparticle. Within that nanoparticle, you're going to have porosity. But then also, between nanoparticles, you're going to have porosity as well. Much of the porosity within these aerogels is actually continuous and fully accessible, which is one of the things that makes them very amenable for things like energy storage or catalysis. But some of the other morphologies that are common for aerogels is this sort of a sheet morphology. You can have this more sort of a ligament, sort of spaghetti sort of a motif. And then here again is just more of that, more of a string of pearls, more of just particulates. The way in which most aerogels are made are using solution gelation or sol gel chemistry. The way in which that works is you're starting with a liquid in which you have your reactants fully dissolved. As those reactants start to interact with each other and react, they form these very, very small particles that stay suspended in the liquid, and so that forms what we call a sol or a colloid. From that colloid, you can actually take that and do various processing steps in order to get to things like coated substrates, thin films. You can start to draw them as a fiber. Or you can just directly dry them into a powder, which you can then use for various other applications. But typically, the way in which I've been going about using these is to allow that sol to continue to react until those particles actually form their own network and form a solid gel within the liquid. And so when you have this solid gel network within the liquid, you then have some various options in order to get a dry material. You can directly dry that ambiently. And what will happen is, because the pores, as I mentioned before, are very small within the gel, you'll get a collapsing of those pores due to capillary pressure as you're drawing off the liquid. And many times we do that on purpose to get a condensed structure, which we can then, center to full density to make, very dense ceramics. Or if we actually want to maintain that porosity, because we want to use that for the final application, you can do something called supercritical drying. And the way supercritical drying works is that you would take that liquid, you would heat that liquid and raise the pressure of it to take it into the supercritical regime. So it's no longer a liquid or a gas. It's a new regime called supercritical fluid. And you can then follow that within the phase diagram. Once you're in the supercritical regime, you're no longer a liquid or a gas, you're supercritical. And then if you simply drop the pressure while maintaining the temperature, you can move that from a supercritical fluid to a gas. And so it's a way to basically go from having a liquid between your within the pores of your gel, to the supercritical fluid, and then to a gas, which then as you release the pressure, you are basically just letting the gas go, and you're able to avoid the capillary pressure that typically would happen if you were just to directly evaporate the liquid. And so when you do that, you are essentially replacing, this liquid with gas, so you don't get capillary pressure, no collapse of your pores, and you're able to maintain that 3D structure in your aerogel. And so this is the typical way in which these aerogels are made. Here at Lawrence Livermore National Lab, we are, it is actually one of our core expertise is in the area of sol gel, air-based aerogels. We have actually pioneered a number of different aerogel materials here at the lab, and are currently, as you can see here from this periodic table, are able to make aerogels based on many of the materials in the periodic table, whether that be in the form of oxides, in the form of pure metal foams, as we can do in some of these cases, and as well as making organic or carbon aerogels, which is really where I'll be focusing on. And if you're curious as to what the interest that Livermore has in aerogels, they're just listed down here. As I mentioned, the National Ignition Facility, many of the targets that they're firing at with these lasers are aerogel targets. You also have energetics, explosive composites that are based on aerogels, various optics we can make actually using the sol gel process I mentioned, making dense ceramics, and then also sensors, coatings, fuel cells, as well as supercapacitors and battery electrodes, which we've moved into recently. Here's just a quick timeline. It's kind of just showing the history of aerogels. Aerogels are actually a fairly recent development. They're developed back in the 1930s by Dr. Kistler, and they're primarily at that point used as scaffolds for catalysis. And through the years, we've had different types of aerogels developed. The organic or carbon aerogel here was developed back in the late 1980s by Dr. Picala here at Lawrence Livermore National Lab. You have several, I think, milestones or highlights here that were developed at the lab. The lowest density material ever created, at least back in, for a long time, since 1990s, was a low density silica aerogel with about 1 milligram per cubic centimeter density. It was actually in the Guinness Book of World Records. We've developed, the metal aerogels famously here at Lawrence Livermore National Labs, as well as, things such as the graphene aerogels, boron nitride aerogels. In 2013, that's when the lowest density aerogel now became a carbon aerogel, which was developed by Sun et al. And then here, we've actually developed this capability to actually 3D print aerogels for use in things such as batteries and supercapacitors. So here is just kind of a highlight of some of the novel properties of aerogel materials. There was a program by NASA back that was focused on basically trying to collect dust from a comet. This was a sort of an application that required a material that was both soft so that the particles that you're capturing would not be damaged, but also robust because you would have to be able to then hold these particles and transport them from space back to the Earth. And so the material they actually chose was a low density silica aerogel. And when I first got here back at the lab, they were actually doing the work of actually retrieving, these dust particles from the aerogel in one of the TMs that was next to, or transmission electron microscopy. It was actually next to the scanning electron microscopy, or SEM, that I tended to work on. They are, the lightest solids on Earth. Again, as I mentioned, low density, ultra low density material. They have very, very good insulating properties. This is because the air does not, transport in general is not good through aerogels. They're very, very tortuous because they are basically made up of nanopores, And so being able to transport, anything, heat, any sort of mass transport through an aerogel is challenging. And here just showing, you can have several 100-degree flame on one side of this, approximately centimeter thick aerogel, and you're not even singeing the petals of a flower on the other side. And then coming more to the application that I work on, they're very, very high surface area. And if you combine that with the high conductivity of carbon aerogels, you then have a recipe for something like a supercapacitor. And back in the 90s, they actually did commercialize the Power Store supercapacitor, which was actually used in the PlayStation, might have been PlayStation 2 at that time. So they are actually commercially relevant. How do we go about making, these carbon aerogels? We use what we call a resorcinol formaldehyde derived process, or sol gel process. And that's shown down here on the bottom. You basically start off with a solution of resorcinol and formaldehyde. You add in a catalyst that can actually be either a base catalyst or acid catalyst, depending on the actual final morphology that you're looking for in your aerogel. Then if you were using a base catalyst, you would end up with, this sort of a clear, translucent, orangish, sort of a wet organic gel, which when dried and then heated at, over about 700-800 degrees C under nitrogen, will give you a final carbon aerogel. And one of the reasons why, we really like this particular method for making these carbon aerogels is that it gives you a lot of flexibility. You have flexibility in terms of the synthesis in order to tune the final morphology. So, things like the pore size, the surface area, the particle size, the density. But then you also can start to incorporate different sorts of nanoparticles, for example, graphene oxide, in order to end up with a graphene aerogel, which has a very different morphology and different properties from the carbon aerogel I'm showing here. So when working with the graphene aerogel, we tend to start with a graphene oxide suspension, so GO. And graphene oxide is basically, if you were to take graphene, which is basically a planar sheet of carbon with this hexagonal sort of structure, and functionalize it with various oxygen-containing groups, such as carboxylic acids. It's many of them shown here in the GO powder from this NMR spectrum. You have, carbonyl groups, you have hydroxyl groups, you have some epoxides, and this is what actually makes the material easy to get into things like water, because otherwise graphene would not want to go into water. But it also allows us to cross-link our GO in order to form it into this three-dimensional network. So what we can do is we can use that resorcinol formaldehyde chemistry and couple that with the functionality, or actually just use the functionality by itself at a high enough concentration of GO in order to form our gel. And so here is just following, using NMR, what's going on, starting off with, your GO powder, which you put into liquid. You would add in a base catalyst. And what you would find is, if you did NMR on this gel, is that you have removed the epoxide and hydroxyl functionalities. and you have this sp3 carbon peak now appearing. Now this sp3 carbon, if you then go do hydrogen NMR, you would find that these are actually methylene and methylene oxide sort of bridges, which are analogous to what you see when you're actually making a resorcinol formaldehyde gel. And when you then take that gel, you dry it, and then you heat it in order to remove the organics and just have your carbon left over, you see that those peaks go away because you're now removing any sp3 carbon and are only retaining the sp2 carbon. And so if you now look at the morphology of this particular carbon gel or graphene aerogel, you would see that you have more of this sheet-like morphology that you would expect from a gel that has constituents that consisted mainly of graphene oxide or graphene now that you remove the oxygen functionality. And then if you looked at the properties, you're able to see very large surface areas, good electrical conductivity. You can get to very low densities. And in this case, these materials are actually very compressible as well. One of the reasons, again, that we like working with the sol gel chemistry is that you can actually tune many of the properties by tuning the density. And so for most porous materials, things such as the mechanical properties such as stiffness or electrical conductivity are tied very, very tightly to the density. Excuse me, it actually is a superlinear sort of a dependence. And so here, if you're looking at a log scale of your electrical conductivity as a function of density for both carbon and graphene aerogels, you can pretty much draw a straight line between low density as you move into higher density materials and track their the electrical conductivity. What we found, though, is that with the typically with many of the carbon aerogels and even graphite carbon, the orientation or the way in which your the defects really within the carbon play quite a role in what that baseline conductivity is. And so that's what really accounts for this difference between basically your more disordered carbons here and your highly ordered carbons, which be more of your graphenes up here, and that you do get this offset in terms of the conductivity. And what we've shown here is, if you can actually densify this, we were able to densify a graphene aerogel to about 1 gram per cubic centimeter. You can actually stay on the line of what you would expect for getting to thermally reduced nano, like an actual just sheet of 2D graphene. So this was exciting for us because it was showing that we're actually able to see some of the properties that typically you only see at the nanoscale, but we're actually able to see them at the macro scale in something that you could actually handle with your hand. And actually build into or incorporate into, a large scale, a macro scale device. Another way in which you can really control the properties, which I alluded to, is the crystallinity of your aerogels. So here is really showing Raman TEM and transmission electron microscopy and Raman spectroscopy for our graphene aerogels. As you can see from the TEM, the sheets are clearly very wrinkly and lots of curves, and which suggest a fair amount of defects. And then if you look at the Raman spectra, that's really confirmed in that you're seeing a large D peak, which is indicative of defects. And the large full width half max here also points to that you have fairly small domains as well. And so when you then take this material and you heat it at in excess of 1500, 2000, or even 25 and 100 degrees C, you actually start to anneal out those defects and get to this very highly crystalline graphene, which you can now actually look at at really the atomistic scale and see how highly crystalline it is. You have much larger domains of single crystal graphene, and that is evidenced here in the Raman spectra, but also it is evidenced in the properties. So in the next slide here, you're able to see that the conductivity goes up, very significantly. And then you also get a slight modest increase in the modulus as well. And so this is just showing another way in which you can really tune the properties. So now just moving to some of the applications. So here showing, we're able to use these materials for lithium ion electrodes or lithium ion batteries. In this case, we're able to deposit various metal oxides, which are good storage materials for lithium oxide, onto our conductive graphene aerogel and get fairly good performance from them. And so we're really leveraging the fact that we have this high surface area and the conductivity to get to, good lithium ion capacity, as well as, good cycling. So the fact that we can, run this through several cycles, increasing the scan rate, and then, drop the scan rate again, and are able to maintain about the same capacity, is showing that it's a fairly stable material. We're also looking at using these materials for electrochemical double layer capacitors or supercapacitors. And so here showing the effect that, increasing the thickness of these electrodes has on the performance. If you have a very thin electrode and you're running it here, sorry, let me quickly explain this plot. So energy density is how much energy you can store. Power density is how fast you can charge and discharge it. If you have a fairly thin electrode, you're able to charge and discharge it up to very, very fast rates without having a large fall off or drop off in terms of the amount of energy that's stored. However, if you go to a very thick electrode, in this case, we're talking, on the order of about a millimeter, you very quickly will see that as you go to faster and faster scan rates, you have this very quick drop off in terms of your performance. And so the reason for that is that these aerogels, as I mentioned before, are not very good with transport. And in this case, it's charged species transport. And as you go to thicker and thicker electrodes, you're not able to actually access all of your electrode, because in the time that you're trying to do these fast scans, your charged species are not able to get in and out of the full thickness of the electrode. So we chose to attack that problem using 3D printing. We believe that we can define the architecture of these aerogels. They're primarily made up of these very small, fine pores, which are difficult to navigate and are dominated by diffusion in terms of their transport. But if we can move to larger pores and really engineer what we call macro pores into the aerogels, we can then start to have more of a fluid flow transport regime, which allows us to have much faster mass transport. And so here just showing some background of other groups that have also worked on, different versions of graphene aerogels, which, I would point you to these papers and various reviews in order to look at. But the technique that we're really focusing on is one called direct ink writing. And the way in which it works is that you have to develop an ink that has the proper rheology. And so this next slide really shows what goes into that. So you need to have a fairly viscous ink, not too viscous such that it can't flow through a nozzle, but you want it to be viscous enough so that it's really something like toothpaste. When you push toothpaste through the tube, it flows out like a liquid, but then once it hits your toothbrush, it then very quickly goes back to being a solid and doesn't, run off of the toothbrush. And that's the exact sort of rheology. It's called thixotropic behavior that we're looking for our inks. So we go about achieving that by, one, increasing the concentration of graphene oxide, or these nano sheets within our suspension. We also add in some fumed silica, which are these silica nanoparticles. And currently we're also working with other modifiers as well, such as various polymers and carbon-based viscosifying agents. And then you also want to have a fairly good yield stress. And so by increasing the geo concentration as well as these viscosifying agents, we're able to increase both the viscosity and get to a high enough yield stress such that we can print the ink. And so here's a quick movie showing the process of making one of these aerogels. So just in this ink, we have, these nanoparticles in the white. You have your graphene oxide sheets in there as well. And then, the rest is basically water. Oops. So the way in which direct ink writing works is you start off with this ink, you put it into a nozzle. You then force the liquid through the nozzle. It comes out as a liquid, but then once it hits, comes through the nozzle and is no longer being sheared, it goes back to being a solid. We do this into a liquid such that the liquid within our gel or within our ink does not evaporate and cause premature restacking and shrinkage. So we can take it through the regular process for gelation, drying, carbonization. Because if we decide to use silica in there, we don't want that in the final material. We can remove that using an acid etch. So shown here, exposed to HF acid, hydrofluoric acid, you can remove it. And then dry your material, and you now have a material that is low electrical resistivity and also fairly compliant, and is basically the properties that we'd expect to have from a aerogel. Here just showing the process of doing this in real time. So it's coming through the nozzle, it's able to extrude, but then go back to being a solid and maintaining its shape. And here just showing some of our early data that we were indeed able to now have here again, energy density versus power density, having an electrode that is fairly thick. Again, this one is 1 millimeter thick. But because it's 3D printed and the ligaments themselves are only on the order of a few hundred microns, you're able to push to very high, to high power densities without having that fall off that you typically would get with a thick electrode. We're continuing to push the boundaries here, getting to even smaller macropores. Our target really is in that 1 to 10 micron range. And so this is work that one of our other scientists is really focused on. We wanted to be able to actually boost the overall capacitance that we can get to. And so here's one way of doing that is adding a pseudocapacitive material. So this is the material that has a much higher capacitance, but is an insulator. So you don't want to use it by itself because it then would be very slow because of the high resistivity. So we put that onto our 3D printed lattices. Here showing, we get very good growth again because we do have this in a 3D printed form and are able to get to very high capacitances with this material as well, and push to higher power densities without having a serious degradation in terms of the energy density. Here just showing some of the physical properties which I've alluded to before. Interest of time, I'm just going to skip some of these. So moving forward, as I mentioned, we're trying to do some modeling and optimization to actually design. These are some very simple, structures that we're coming up with right here, but we'd like to actually get to some more advanced structures. And so direct ink write, which is a tool path limited method, isn't really going to get us to, really interesting and complex sort of architectures. So we need to have really a whole new 3D printing scheme in order to do that. And so that is why we moved to what we call projection microstylithography, which is a photochemical method in which, if I play the video here, you're starting off with a file that is a computer CAD, for example, a CAD file, which you then divide into slices. Each one of those slices you can then project onto a photocurable resin. So here just showing the image going through the optics, And then, you project different slices at different levels of the resin as you're lowering the platform in order to build your 3D structure. But of course, in order to do this, you need a resin that is UV curable. So here we're working with a professor at Virginia Tech, who's since actually moved to UCLA, in order to develop a resin that would have this UV curable characteristic, but in the end also give you a material that is the graphene aerogel. And so here's just that scheme, and here just kind of showing some of the finished architectures that we're able to get to, these much more advanced architectures. And when you do this, you're actually able to, as I mentioned before, you have this typically the superlinear dependence of porous materials on things, of porous materials modulus on things like density. But you can actually start to shift that dependence. So here, it's close to 2.6, which is common. Shifting it to something more like 1.5, so it's a much lower dependence now, when you start to incorporate some of these complex sorts of architectures. So moving forward, we're looking to use some of these materials for things like flow electrodes, reactors, catalysis, and desalination. I wanted to be able to leave some time for questions, so I'll just also mention we do a lot of work as well with sensors, so looking at being able to sense gases in particular. And we work with a lot of different materials in order to do sensing of gases. This is work we do with Professor Zettel and Mabudium at UC Berkeley. And I think with that, I will jump to the summary slide and open it up for questions. Oh, we can't hear you, Juana. I think you might still be muted.
Okay, all done. So this is the summary slide.
Yes.
The great work that you do at Lawrence Livermore National Lab. So we thank you, Doc, for your time. And thankfully we had to have you virtually because, we moved you since you were coming in, was it March for the seminar? I think you were coming the week after we actually got shut down and quarantined. But we're glad we made it up. Fascinating work that you're doing there. Before we open it up, there's some people that were coming in and dropping out. So what's the difference with UV curing for the new resins you have versus UV curing like it as you direct ink write? What's the difference in the type of processes if doing it with, DIW versus the new process you started doing?
Right, so that's a good question. So with the direct ink write, you actually don't need UV curing. Because the inks have this thixotropic property in which while you are shearing them, as they go through the nozzle, they're experiencing a high level of shear. So they flow like a liquid, but the moment you remove that shear, they recover their solid-like behavior, or solid-like rheology. And so you don't actually need, if you design your ink properly, you don't need UV curing in order to get a good direct ink write ink. However, with projection microstereolithography, it is a critical requirement that your ink is UV curable because you're using light in order to solidify your material, your part. Okay.
So yeah, one of the reasons I'm asking is because we actually bought some new printers right before COVID, and we have the option to UV cure, in the process. But we do a lot of hydrogel cross-linking work from my stint there. So it's going to be interesting. Whenever we can get in there again, to see, you know, the inks we can actually make using that process. So really cool, fascinating work. Where do you think the the space for aerogels will go? Where do you see this still going now? So I see the progression where nanoparticles and, you know, I would say perfusion, if you will, with, you know, trying, like you said, oxygen not penetrating through it. And then you guys have developed it, allowed that to happen more. You can kind of start to essentially model this. But where do you think the next big thing will come, you know, given you can make things denser or less dense, should I say? Where do you see the field for the aerogels moving into now, that space?
Yeah,
Next.
so right now, I think that, and one of the areas we're really pushing on is this area of 3D printing, or basically trying to find ways to essentially get around the traditional limitations of aerogels. So transport through aerogels is one of the things that, I mean, it's used as it's actually an advantage for things like insulation. But in energy storage, in energy conversion, where you actually want to push a lot of fluid through, for example, an aerogel, so that it can actually interact with the high surface area material, the transport is actually quite limiting and quite a challenge. And so, you know, being able to use things like 3D printing to get around those issues and to try to decouple some of that, I think is one of the areas that we're pushing in. And then on the other side of it as well, from just a mechanical standpoint, when you go to these very low density materials, the mechanical properties tend to degrade. And so one of the areas that we're also pushing in is, you know, trying to augment this for not just the carbon aerogels, but, you know, many other aerogels as well, so that they have the requisite mechanical properties to stand up to whatever applications we're envisioning for them. But I mean, you know, that's the expanding of the 3D printing. But in terms of actual applications, it really is looking at using them in things like, you know, batteries, supercapacitors again, getting into some bio-related applications. So using them as scaffolds for, you know, growing cells, for example. We have work going on with Professor Sabri at University of Memphis, trying to grow nerve ending cells, for example, onto the carbon. And we're seeing some exciting work because carbon is actually conductive. You can actually kind of control the growth or have some influence on the growth by, you know, putting a voltage across it, which is kind of exciting. And then for desalination is another area. Water security is another area that we really work on here quite a bit. And the last few years we've had work with the state of California trying to develop desalination, capacitive desalination based on some of our carbon aerogel technology.
Awesome, awesome. Thank you. Yeah, that's why I was asking for ideas for my resubmission of the proposal. Where could we walk into that? All right, so I'm gonna open the floor for questions. I think Dr. Lawrence has a question next. Unmute, Brian.
I realized I was muted. So thanks, Dr. Worsley. This was great. I wanted to ask a question because I'm looking at a lot of the materials that you're choosing to print with, and it seems to me that a lot of them already have applications that exist outside of being aerogels, right? So I see graphene. I see you've got a lot of different sulfides that have functioned in you know, FETs and OLEDs, OLEDs, and things like that, which I think is great. I mean, it's a great place to start from. But the question I'm wondering is, because the 3D printing framework gives you the opportunity to introduce new geometries, and this is in part for our students because they think about, you know, chemistry. How is this involved here? To what extent, when you're thinking about material design, do you consider what is the material and then how does that fit into the 3D shape that I actually want to print? I mean, are you looking at it from that standpoint, or are we just not quite there yet in terms of our theoretical models applied to our actual material mechanical applications?
Right. So that's a good question. And if I'm hearing you correctly, is it really you're trying to suss out, why do we print what we're printing, regardless of the material, or how do they interact?
So some of both. So
Okay.
it's almost like, why do we print what we're printing out
Mhm.
of what we're printing it with?
Right. Right.
Does that make sense?
Yes. Yes.
Right.
No, I follow. I follow. So the reason why we started looking at the graphene aerogels or carbon aerogels for energy storage is because we knew that they were very good at being conductive and having very high surface areas. But we ran into a problem in terms of, we were thinking it'd be nice if you could have an electrodes. Typically, supercapacitors are, made in like very thin layers, and they have a lot of. You have to have a metal conductor or a current collector, which does not contribute at all to the capacity of the devices. It's pretty much wasted volume and wasted space. And so we were thinking, if you had an aerogel that is already conductive, and if you could actually have it basically volume fill, like, you would have full use of the volume without having to sacrifice, having dead space or dead weight. But the problem that we ran into was as you tried to make the aerogel thicker, the performance was degraded. And so that's what started to dictate, the sorts of architectures and designs that we printed. We were asking the question, okay, we see where these things are good, but we also see their weakness. How can we print them or design their architecture in a way to get around that weakness or to minimize that weakness? And so it's really looking at whatever material you're working with, seeing its strengths, but also recognizing its weaknesses and asking the question, what can we do in order to really address those weaknesses, such that it would actually make this, this material or this idea more viable.
Gotcha. Thanks for that. I appreciate it.
Yep.
Do we have any other questions from any of the students logged on?
No, great presentation. Thank you so much.
Thank you.
All right, well, for the sake of time and time zones, we want to thank our speaker again, Dr. Marcus Worsley from Lawrence Livermore National Lab. This is being recorded. I hope you're okay with that, but I know all your stuff got clearance as well, right, Doc? So we're good.
Yeah, this is fine. And I also just want to, if there are questions, because I know you are recording this, I believe my email should have been on that first slide, but you have my email, Professor Mendenhall. So you feel free to, put that out there if anyone does have questions related to the presentation.
Okay, will do. And yeah, so this was really great, and we will circulate this, and I will tag your email to it in case there are any other questions. Again, I unfortunately you can't be in person with us, and we were excited to have you back in the spring, but when we come out of it, we're happy to have you back in person and keep things moving forward. But until then,
yep, be excited to come back.
All right, thanks so much, Doc. Everyone, have a good night. Stay safe, and we'll chat again soon. Okay.
All right, thank you.
Thanks, everybody. Have a good one.
Bye.